In some cases, it makes sense to transform a variable x by a linear factor. Right? So we're going to learn what happens when you manipulate data using a linear relationship. Right? And so there's value in that because, for example, if I know the mean and standard deviation for, let's say, a set of temperatures in Fahrenheit, how would that translate to the mean and standard deviation for the temperatures in Celsius? Right? Because it's a linear transformation to get from one set of units to the other. So it begs the question, can I just manipulate the mean and standard deviation for one set, so the Fahrenheits, and the result will give me what I'm looking for in Celsius, or do I have to do the transformation to each individual data point? All right. So I'm just going to give you a basic set of information here. So let's say we have a data set, very small, that contains the values, we'll call it x, 1, 2, 5, 7, 7, and 12. All right. 1, 2, 5, 7, 7, and 12. So nothing too crazy. Then from there, what I'm going to do is create some sort of transformation. All right. So in this case, I'll say that the transformation is 70 plus 2/3 x, poor quality thirds. For some reason, you'd have some reason to transform your data. You don't do it just for the heck of it. Although you're working on a misleading graphs project, so maybe you're coming across some situations where people are transforming data just for the hell of it. All right, but what we would do here is run through the operation, substituting each one of these x values into the function, or in this case the expression, and coming up with the transform values for those x values. All right, but we want to use technology to our advantage, so I'm going to use Desmos. I'm going to pop in a table. I'm going to use x1 instead of the x because Desmos understands x to be a variable. All right, so it's going to treat it like a function. All right, so it gets confused if you just use x. So we use x sub 1. All right, so I put in the values, and then in y1, what I'll do is I'll just type in 70 plus 2/3. Instead of x, I'll say x1. All right, so it'll give me all the transform values. So what I want to do here is I want to find the mean of the original set of data. All right, so I'll find the mean of my x values. All right, I could do that again in Desmos by just using the mean function. So function, stat, mean, or you could just type in the word mean. All right, it'll know that it's a recognized function. So if you type in, you start typing in MEAN, it doesn't know what you're doing, but then once you get the n in there, it locks it in as a recognizable function. Find the mean of x1. So it'll give you the value. I'm going to convert that into a fraction just so I don't have to worry about rounding, so 17/3. And then we'll also have the standard deviation of those x values. That I don't want to type in, so I'm just going to go into functions, stats, and then select standard deviation. Now just be careful, in function stats, there's also standard deviation with a p. That's population standard deviation. We don't want that. All right. That's only if you know that you're working with an entire population, which we don't know. All right. And if you're in doubt, you go with sample. All right. The sample is the one without the p. All right. So standard deviation of all the values in x1, and you have this. I will have to round because it doesn't give me the option to put it as a fraction. So 3.983 approximately. All right. Now, what I want to do is I want to look at what's going to happen to the mean and standard deviation after the transformation. All right. So going back to all these values, I mean, I could put it all in. I could just kind of approximate it. 70.6 repeated. not really, that's actually an exact value. 71.3 repeated, 73.3 repeated, 74.6 repeated, twice, and then 78. All right, so what I would do, instead of typing in all those values as a separate computation, I would just find the mean of that transformation, which is 70 plus 2/3 x1. All right, so this is telling me that the mean of the transformed data is about 73.8 repeated. Okay, so what we get from this, I mean, it might not be obvious, but if you were to run the mean through that same computation, so if we were to do 70, or compute 70 plus 2/3 times x bar, all right, that's what this would be. That's 17/3 x bar. If we were to compute this, we would get the same value. All right, so I'll show you real quick, but it's telling us that we can use the same transformation on the mean and come up with the same answer that you would get if you transformed each individual data point and then found the average of the results. All right, so in this case, I would say 70 plus 2/3 times the mean of my x1 values. Oops, I hit equals accidentally. You see, you get the same value, 73.8 repeated. All right, so then we would look to see if that's what would happen for the standard deviation. All right, so I'm going to compute the standard deviation for the 70 plus 2/3 x1. All right, and so just to be clear, what I'm computing is the standard deviation of these values. All right, these new values, which are represented by 70 plus 2/3 x. So we're looking at approximately 2.656. All right, so what I would be asking myself is that the same as running this number through this computation? All right, so would it be the same as saying 70 plus 2/3 times the standard deviation of the x values? All right, so we'll take a look. So 70, I mean, you should be suspicious because it's just a 2.656. It's not 70 point something or other. So, but aside from that, 2/3 times the standard deviation of the values in x1, we would, if we ran it through that computation, we would get 72.655. That's nowhere near the 2.656. However, if I get rid of the 70 plus, we get exactly that number. All right, so what this tells me as a shortcut is if I want to find the standard deviation after a linear transformation, I don't need the 70 plus. All right, because that 70 plus is a shift. It's a shift of values. If you think about a standard deviation as how spread out a data set is, just shifting every point over isn't going to increase or decrease the spread. So if I have a number 1 and a number 2, increase them both by 70, they become 71 and 72. They're still separated by 1 unit. All right. The thing that will impact how spread out the data is or are would be the slope. All right. So the multiplier, because if you actually think about it, and it's the connection to geometry that never really happened and it kind of sucks, but that's actually, kind of a failing in the whole system, but that's a different story. Right? So you'll learn about all these different transformations in geometry, like dilations, reflections, rotations, translations, and all that. A linear equation is a dilation followed by a translation. All right? The dilation is the slope. The translation is the y-intercept. All right? Because what happens is a linear equation normally starts off at 0. In this case, I'm telling you to start it off at 70, so that's an upward shift of 70 units. Normally, the spacing represented by the slope is 1. Rise over 1, 1 over 1. I'm telling you, forget that, make it 2/3 of that spacing. All right, so a dilation factor of 2/3. So the slope is impacting the spacing between points, all right, which naturally impacts, if standard deviation is a measure of the spacing between points, the slope is naturally going to impact that. All right, so that would be the only thing we would care about for the standard deviation. The mean is very sensitive to a shift in value in terms of movement, but the spacing is impacted substantially by the slope. All right. So the next page, you're going to want to memorize all these rules. All right, you will be assessed on these, so I'm going to put a big star on this. There's nothing really to go over here. You just got to know these rules. All right? Know these rules for the first unit test. All right, very important. Oh, consistency in my stars. All right, not to be confused with the summer review prerequisite test. All right, when I say the first unit test, I mean the unit test for this unit, for unit 1. All right, so I don't know if it came through as an announcement or whatever, but there will be, it should be in the updates, there will be a test. It was supposed to be like a couple weeks ago, but I never really planned that out very well because like with the days off and all that. The prereq test, from the summer assignment, that's going to be on Monday, or this coming Monday. All right. So if you haven't reviewed the material in that summer assignment, make sure you do it before then. If you have any questions, make sure you ask before then. Yeah.
What's that test going to look like?
So it's going to be 4 short answer questions, quick hitters related to those function questions like composition of functions and linear equations. And then the remaining 6 questions, I'm going to give you a data set, and I'm going to ask you to find things, just like in the summer assignment, find like the mean, the mode, and any outlier, box plot and histograms and stuff like that. All right. So that's all stuff. If you want, you could do it on Desmos. You could do it by hand. I'll give you the option to do either or both. It's you got a lot of wiggle room there.
Yeah, that's what I was going to ask. And it's just on the summer work, not what we've done so far?
Correct. Just on the summer work.